Hey, hello guys. So this is the video that introduces you to chapter 5, chapter 25, titled Capacitors. It should be part of the video series for class today. Um, my previous video, I have to say, that was the very first time ever that I would use the Camo Studio to make a recording. I've never seen it before, and yeah, I made a bunch of mistakes, but I don't have the time to go back and re-record. So just bear with me on that. You still get all the information that you need. Okay, so you should watch the first video first, the video that covers the homework problems, the approaches to solving the homework problems for chapter 24. And then after that, when you're ready to dive into chapter 25, then you should watch this video. Um, Also, before you watch this, remember our discussion about Elon Musk? I sent you two links. The first one is how he had purchased a super or ultra capacitor company and lost money, but he was very happy with that because to him it was just about understanding how supercapacitors are made and making better ones. And from his buying that company and working with it, his team were able to develop a new type of battery. Um, New, quite great advancement in battery technology using those ideas, and they Elon gave a battery day as one of the stakeholders meeting that he had in, I believe, 2020 or 21. Yeah, but that was the second link that I sent you. And I want you guys to just watch the video, learn about the new technologies, learn about the electroless battery and how it was able to increase the energy density to make them much better batteries for EVs. So yeah, it's nice for you to go through those materials, and then you learn about capacitors in chapter 25. How did we get here? We started the course, and at the beginning we decided to learn about charges, what they are, what their properties are, and how do they move, and what can we make from the knowledge of charges, their properties, and how they move and interact. So we learned there are two types of charges, and charges are conserved, they are quantized, and like charges would repel and unlike charges would attract. When they repel and attract, they do so um, due to the electrostatic force of attraction or repulsion that is given by Coulomb's law. That was chapter 21. In chapter 22, we talked about how these charges set up electric field. So you learned a lot about electric field, how to visualize electric field, how to calculate electric field for different configurations of charges, from a point charge to a dipole to line of charge to a charged ring disk, and so on. And then in chapter 23, you were introduced to another way of calculating electric field using Gauss's law. So Gauss's law relates the charges enclosed by a Gaussian surface to electric field at that surface. You guys learn about the Gaussian surface, then how to apply Gauss's law. You learn about flux, and you were able to go from Gauss's law to Coulomb's law, and you should be able to go back from Coulomb's law to Gauss's law. What I mean is that you should be able to, starting from Coulomb's law, derive an expression for Gauss's law and vice versa. So that should put your mind at peace that Gauss's law is not some crazy idea. It's actually rooted, deeply rooted in what you guys have learned from Coulomb's law. So after that, we studied in chapter 24 the electric potential. So we identified that electrostatic forces are conservative forces, so they do have potential, and then they do work, and the net work done within a closed loop is zero. So we were able to use the work potential energy theorem to derive an expression for the electric potential energy, and then we use that to define the electric potential as electric potential energy per unit charge. So, and after that, we wrote some equations to help in calculating electric potential. We brought up the idea of bringing a charge from infinity and defining changing potential. We learned about the different potentials and the equipotential surfaces. So after studying chapter 24, we solved some problems. Well, you guys should be solving the problems, the homework problems that my last video kind of addressed. Okay, so now chapter 25 is titled capacitors. I'm gonna try to write some notes here. Capacitors. What are they? So capacitors are the devices that store charges. Why do we need to store charges? Well, we now know from chapter 24 that when we cause charges to move, we actually do work. And we want to do work, we need energy. So that's the whole reason why we should store charges. Now, I want you guys to be able to differentiate between a capacitor and a battery. The main difference is actually few differences. Batteries store charges chemically, and they don't have as much ability to release energy, a lot of energy at the same time as much as capacitors do. So that's really what differentiates capacitors from batteries. Batteries are good for, applications that require you utilizing energy at a really slow rate. Whereas capacitors, you should be able to, if you charge a capacitor, you should be able to release the whole energy of that capacitor almost at an instant. And that's really what made EV cars stand out now, because when the batteries they used and the better capacitors that are built in them enable the cars to have an access to tremendous amount of energy at an instant. And that's why the rate of acceleration of electric cars now are getting better than those of ICE, internal combustion engines. And you see that in even the regular Tesla that you will buy. You can take that car on a racetrack and it will have better acceleration than the, in quote, sport cars, dedicated sports cars. So yeah, so now capacitors. What are capacitors? Capacitors are devices that we use to store charges. And what is the capacitor made of? So if you do a Google search, I encourage you guys, well, first do a Google search of capacitors and image search. You're gonna see a bunch of stuff that kind of look like batteries, look a little bit weird. But like I said in class the last time, I want you guys to find some really old electronics like transistor radios, VHS. Uh, find one somewhere or buy one at a local thrift store for really cheap and smash it, break it open, and you're gonna see capacitors in there. I think it's really cool. Now we've scaled down the capacitors and we're able to pack more charges, but the older systems will show you those capacitors. It's really cool. Okay, what does a capacitor look like? Basically, a capacitor is you have two conductors, okay, meters. That's meter 1, that's meter 2, and that's it. You have a capacitor. So if you have any two isolated conductors, put them side by side, guess what? You have a capacitor. Yeah. So I think I should give you some notes. Say capacitors are devices that store charge. Guys, the reason I'm giving you this note is I want you to act like you're actually in class. Grab your notebook and start writing all of this in your notes, because when we have the next discussion, we would refer to these notes. Okay. So we need to define a term called the capacitance of a capacitor. If we say that a capacitor is a device that stores charges, then think about it as a container where you put in charges. You want to know how much charge you can store in that container, right? So that for your application, you need to know if you need a big container or need a small container. So the amount of charge that you can store in a capacitor is called the capacitance of the capacitor. So let's write that down. The capacitance of the capacitor is the amount of charge, the amount of charge that you can store in your capacitor. That is stored in a capacitor. Okay. Very soon we will be drawing what we call circuit diagrams, but you would see some of these symbols in circuit diagrams. So the symbol for capacitor is, you have something that looks like two parallel lines, and that's it. The two parallel lines are of the same height or the same length. So that's a capacitor. So that's a symbol for capacitor. And you will see this in a lot of circuit diagrams. As a matter of fact, we'll draw a circuit diagram really soon. But yeah, so that's a symbol. Now, if capacitance is the amount of charge that you can store in a capacitor, that means it's a quantity. And the question is, what is the unit of that quantity? So the unit of capacitor, of capacitance, is farad, F-A-R-A-D, and we just represent that as an uppercase letter F. All right. So the capacitor and charge are related. This way things get interesting. The charge stored in a capacitor and the potential difference between the plates, when I say plates, I really mean the isolated conductors. So let's call them the plates of the capacitor are related like this. Thus, okay, so Q equals CV. So that's the first equation that we use to relate the capacitance and the potential difference to the charge. So anytime you write an equation, you must always know what each of the quantities is. So your Q equals the charge on your capacitor, your C is capacitance, and your V is the potential difference. Potent, I can't spell. Okay, cool. So from this relationship, Q equals CV. If you rearrange, C will be equal to Q divided by V. So that's another way for defining the capacitance. And with this, it follows that the unit for capacitance will be equal to unit of charge is coulomb, unit of potential difference is V. So that C over V is the same thing as 1 farad. So 1 farad is 1 coulomb divided by a potential difference of 1 volt. Okay? Don't let this confuse you. It's not IF. It's 1. Okay. So equals farad. All right. Good. Now, you guys have learned what a capacitor is and how how to represent the capacitance of a capacitor. Let's look at something a little bit more interesting here. If you have a capacitor, we said it's just two isolated conductors brought next to each other. How do you use it? Well, to use a capacitor, you have to charge it first. And then after you charge it, you can use it by releasing the charges and causing the charges to do some work. A very good example is this. Many of you are probably too young to remember, but back then, when I was growing up, we had this disposable cameras. You can go to Walmart and you buy a disposable camera, and you can take, I can't remember, probably 29 photos. So you take pictures, and after that you take it back to Walmart or wherever you got it from, and you give it to them. They will develop the photos, and you go back and you pick the pictures up. Yeah, so if you've ever seen those, there is one interesting feature that those cameras have. They have a built-in flash, but to use the flash, there's a little button that you have to press and hold for a while, and when you press and hold it, you're gonna hear some kind of whine, like, and then a light will come on, and the light will tell you that now you can use the flash. And then as soon as you take your picture, you see a bright flash of light. As soon as you take that picture, if you want to take another picture right afterwards with flash, it's not possible. If you push take the picture, the flash will not come on. You have to hold that button again for some time, and you hear that whine until the light comes on, indicating that now your flash is ready. Guess what is happening in that camera? Anytime you push on the button to hold it down, what you're doing is you are charging the capacitor in that camera, because there's a little battery built in, but that battery does not give enough energy to power the flash. So there's a capacitor built in that anytime you need to use the flash, you have to charge that capacitor. And when that capacitor is fully charged, then you push on you take your snapshot, and the flashlight comes on, because all of the energy within that capacitor is released, and that's enough energy, enough power to power the light. So how do you charge a capacitor? I think that's what I want to discuss with you next, and after that we'll end this video, and then when I come to class I will talk to you about how to calculate the capacitance of capacitor and the different ways to arrange capacitors in series and parallel, and we'll look at different types of capacitors, parallel plates, cylindrical, spherical, isolated sphere, and so on. But anyways, charging a capacitor. All right, I'm gonna draw a circuit diagram, and in your circuit diagram, so you guys will be drawing a lot of circuit diagrams, and you will see different symbols. You should be able to identify what each symbol represents. All right, so this is a very simple basic circuit diagram, and this consists of a capacitor, in this case parallel plate. You understand that in the next section. All right, so looking at this, there are three different components of this circuit diagram. There is your battery, which we would end up calling the EMF device, but for right now you can call it the battery. Okay, there is your switch, and then there is your capacitor. All right, so at the beginning, now the circuit is not complete because you have this switch is opened. You see how this part is not touching this part? So because it's open, nothing goes on in this circuit diagram. Now what we're going to do is we're going to close the switch. We're going to turn on the switch. When we turn on the switch, then we have completed the circuit. And in completing the circuit now, we can charge our capacitor. Now, before we connect this, we have our capacitor, which as we described earlier here, is just two conductors, okay, that are put together. So this is our capacitor, but it has no charge at all. Now we want to charge it. We're going to charge it by using this battery. So this battery has two plates. The positive plate is represented by the longer part, and then the negative plate is represented by, that should not be positive, that should be negative. Okay. All right. So that's positive above and that's negative plate below. Now, each of these batteries, you guys know that anytime you have a battery, it's rated in volts, right? Like you go to Walmart and you want to buy a AAA or AA battery, and you look at it and they say 1.5 volts. What that means is that the potential difference between the plates of this battery is 1.5 volts. And you guys remember in chapter 24 that if you cause charges, in this case electrons, to move from a low potential to a high potential or vice versa, you're doing some work. You've actually calculated the work done. So a battery has releases energy because it's got a potential difference between the plates, and that potential difference can cause its charges to move, and in so doing, um, release energy. So now this battery, let's say this battery is 1.5 volts. The potential difference between the plates. All right. So this battery has a potential difference of 1.5 volts. Our capacitor has potential difference of 0 volts. There is no potential difference because there's no charge on it, right? You guys remember that the charge is equal to the capacitance multiplied by potential difference. If your potential difference is 0, there's no charge on it, and vice versa. So it's not storing any charge. Yeah. So now you connect this and see what happens when you connect this. When you connect the switch, now the capacitor and the battery are connected. But let's look at this plate. So look at this connection. This positive plate is connected to this plate on the capacitor. So think about it. What happens here? This positive plate is positive because it has more positive charges than negative charges, right? So this is positive. It has less electrons. This is neutral. It has the same amount. This plate on the capacitor is neutral. It has the same amount of positive and negative charges. So what happens is that anytime you connect two conductors, and one has higher amount of one type of charge than the other, then the charges would move in such a way to place those conductors at equilibrium, because now you've connected them. Now we have two types of charges, the positive charges and the negative charges. You guys know that the only types of charges that move are the negative ones, represented by electrons. So you think about this plate has more electron, this plate has less electrons. So electrons are going to move from this plate on our capacitor. Electrons are going to move to this positive plate, trying to balance the charges to make it at equilibrium. So when the electrons are moving here, this was neutral, this plate was neutral before the movement of electrons, and then when electrons leave this plate starts becoming positively charged, right? Because it's losing electrons. The electrons are going to this plate. Now at the same time, this negative plate has been connected to this plate on the capacitor that before turning on the switch had no charge on it. I mean, had equilibrium, the same amount of positive and negative charges. So now you have an excess charge electrons here, and so on this plate from your battery, on the negative terminal, you have more electrons than you have on this plate. So electrons will move through this circuit and come to this plate. So as time goes on, this plate is becoming more positively charged and this plate is becoming more negatively charged. And that will continue until a point is reached where the potential difference on this battery is equal to the potential difference on the capacitor, right? Because now this is becoming more positive and this other plate is becoming more negative. So you're creating a potential difference. When the potential difference of the capacitor meaning the potential difference between the plates of that capacitor, is equal to the potential difference on your battery, then you say the capacitor is fully charged. Okay? Yeah, I might just provide you with a picture of my notes that has more description, but I think you should understand the explanation. That's better than having notes. Or, but anyways, that's how you charge your capacitor. Actually, it's not much of a muchness, so let me write it down here for you so you can have it in your notes. All right, I'm gonna erase this part and use it to write the notes. All right, so guys, please write this down and make sure you're able to describe it. You will describe it in an exam. All right, so I'm gonna withdraw the, oops, why am I having blue? Okay. I'm gonna withdraw the circuit. So this is the positive terminal and this is the negative terminal of your battery. B for battery. And then you go here, you have your switch, S for the switch. And then here you have C for the capacitor, and you complete this. Okay, so note that the positive plate has higher potential and we call it the positive terminal. So this is the positive terminal of your battery. And this is the negative terminal of the battery. All right. Negative terminal. Okay, cool. So to charge a capacitor, let me use more space here. To charge a capacitor, connect the switch. Okay, when you connect this switch, the charges flow. And the charges that can move are the electrons. So the electrons will flow. And the electrons flow because the battery has an electric field set up in it. So the electric field set up in the battery drives electrons from plate H of your capacitor to the positive battery terminal. So let's call this plate H on our capacitor, and we're gonna call this L. H for high, L for low. That's it. Okay. So When electrons are driven from plate H to the positive terminal, plate H loses electron and become positively charged. Okay. Likewise, the electric field drives electrons from the negative terminal of the battery to plate L of the capacitor. And plate L becomes negatively charged. So the potential difference in the capacitor increases of the capacitor increases until it equals the potential difference on the battery. dV of the battery, at which point it is fully charged, at which point, meaning that when the potential difference of the capacitor equals the potential difference of the battery, the capacitor is fully charged. Okay, so this will end the session on introducing you guys to capacitors and capacitance and how to charge a capacitor. When we meet next, we will talk about different types of capacitors and how to calculate the capacitance for each of those types of capacitors. Okay, I will see you then.